So my name's Frank Berry. I'm an analyst with IT Brand Pulse, and I'm here to introduce your next session, your next speakers. And there are two speakers from Solarflare Communications. Before I introduce the individuals, I'd like to tell you a little bit about the company. So Solarflare is a company that established itself by providing Ethernet products to Wall Street. The most demanding companies in the world, the most demanding customers in the world. And what happened over the last several years is that the Wall Street customers started to ask for specialized capabilities. Things that you wouldn't need in the enterprise. 1 microsecond latency, super high bandwidth. We need microsegmentation up to thousands of VNICs in a regular old NIC so that we don't have system jitter. And we need super low latency. Who needs low latency? Who needs these features outside of Wall Street? Well, you didn't. But like, I'll use the analogy of NVIDIA, you really didn't need the parallelism in a GPU outside of gaming. But in the new world of analytics, suddenly you need that model. And in a similar fashion, in the networking world, we all know that you've heard it a million times already here today. We're moving to a new distributed environment, and suddenly you're going to hear this term microsegmentation a lot more in the future. So so the building block of a software-defined data center is now the server, and the hyperscales are already doing it. Wall Street's doing it, and the people that are behind it is Solarflare Communications. So. I think what you're going to see here is you're going to see something very different than what you've seen in all the other presentations. So what they've done, based on the work that they've done for Wall Street, is they've already developed fabric services that's tailor-made, ready for NVMe to bolt on, and I think you're going to find it very refreshing. And I don't want to say any more and steal their thunder, but let me introduce your first speaker, Ahmed Hussain, VP of Marketing. Your next speaker is Steve Pope, Dr. Steve Pope, who's the CTO at Solarflare.
Well, one of my problems was coming up to speak here was how do I represent what Solarflare does? Because everybody asks me, what does Solarflare do? So I've been struggling with this and trying to figure out what Solarflare does. So I came up with this analogy about roads and cities. What we do at Solarflare is we are traffic engineers. We define how these cities and traffics are implemented together. That's what we're all about. How do you make networks and infrastructure work most effectively? So the analogy I like to use is we're traffic engineers, and so I'm going to talk a little bit about that. So when you look at the environment we're in, and especially to the applying this analogy to NVMe, today NVMe is building this beautiful performance car. It runs fast, it's very effective, it will do light speed, it will do all those wonderful things. But at the end of the day, the issue here is it could be very fast and very effective, but you have to run it on a special racetrack. So unfortunately, our data centers don't have special tracks. They're built just like your city. Lots of lanes, lots of avenues, lots of congestions, lots of issues driving all around your network. That's the problem that we face, taking something like NVMe over fabrics into the new class of data center. Not only are these data centers complex and very sophisticated in terms of networking, but there's a lot of traffic engineering goes into making those data centers run effectively. So a simple thing as like a crossroads in the city, there's a huge amount of work that goes in to make sure that crosswalk and the human beings and the cars all flow effectively. So that's the job we've been working on, is how to make that most effective. And if you look at it, not only is this complex environment, but we computer bots have been developing virtualization layers that take it to another dimension above that complex style of cities. You never have virtual cities really these days, it's all physical. But think about a data center network is completely virtualized, not only at the physical layer, but all the way up to the application layer. So virtualization is a big issue. Not only that, building this environment, we have to scale it. So our roads and infrastructures have to take in trucks, they have to take in SUVs, cars, pedestrians, cyclists. The ability to scale that effectively is a real huge engineering effort. In the same way, a data center is in the same manner a complex environment where those have to be taken into account. So scalability is key for a well-balanced data center. And the reason I bring this subject up, because a well-balanced data center that works most efficiently does not create bottlenecks in there. It works very effectively. So this ability to scale a data center is critical to the workloads. Not only do you have to make this all work, but you have to be able to monitor it. So what's going on in each junction, each point in your data center? So visibility of your data center in terms of telemetry, packet flows, how things are flowing in and out, but not only in the physical wires, but also inside your server is a critical aspect of your data center. So we have to take into account the visibility aspect, the view. Not only that, we have to figure out there are certain applications and data must move across our infrastructure fast. So we have the ability to accelerate. In the same way here, a carpool accelerates certain class of traffic. All this complexity is also confounded with recently with all the security issues inside a data center. Just like roads, we put roadblocks and security checkpoints up to prevent things going in and out. The same way, the data center has to be built with that in mind, an infrastructure. In our modern data center, implementing security is a key aspect of solution, not only in the perimeter of the data center, but inside the data center. So, how do I map this into the new direction? So we talk a lot about neural class networks. So I'm going to go to the work we've been doing at Solarflare since 2001. After 9 generations of development, we have come to a point where we have some core technologies. And we think this neural class fabrics is the point in the infrastructure. If you look at today, very simply, this is a Facebook picture you may have seen. They have over 1 billion users worldwide connected in their infrastructure. One of their biggest problems is the flow of traffic inside the data center. So this is growing exponentially year over year and will continue to grow. And also, if you look at artificial intelligence, when you apply artificial intelligence applications to this big infrastructure, you're creating thousands of parameters and thousands of instances that are going to calculate, like in this example, a face recognition piece of software, defining whose face it is. All this is creating what we call the neural class fabrics. So if I wanted to take another look at this just to amplify, because there's something else changing in the data center that's making this infrastructure scale and grow in such a dramatic fashions. If you look at 2005 and look at a traditional rack, and on average on that 38 servers you may have connected, you may have had 38 connections connected, one per each server. And in that server you may have had a single CPU with maybe 2 CPUs, a single server with 2 CPUs. Maybe there was a couple of cores in each one of them, so that may be 8. So the number of instances running in parallel was not a big deal to a rack of servers. But when you look at 2017, the number of connections and instances we're running is huge. And this creates a lot of growth inside the rack of servers in terms of connections. And this is where we sort of take the analogy of a neuron. Neuron can have up to 10,000 connections. So any point in our rack can have up to 5,000 endpoints that it could talk to any moment in time from an application perspective. So this is where our term neural class network came from. So let's do the math. How did we get here? Well, you'll hear this term a lot. Moore's law is going away. It is, to a degree. The frequencies are not growing as fast as we would like it to. But the thing that has changed dramatically over the years is the number of cores per chip, per CPU on x86 and many others is growing substantially. So if you do the math here and you take 2 processors at 32 cores each, you multiply that by 2 threads, you multiply that out in terms of connections, you can end up with a tremendous number of connections per server. So these cores all want to communicate with each other. And I don't mean directly across the network. So they create this massive growth of number of things that have to happen concurrently in parallelism. So parallelism in the data center, in the network, is becoming a substantial requirement and driving some innovation around this space. So the other thing, we talked about security. In this example, not only do you have to have security rules on the outside of the data center in terms of firewalls and policies, but you have to, in a data center of the future, you have to have policies that manage how data flows inside it and making sure malicious things don't get inside your data center. So the ability to secure every endpoint inside your data center becomes a critical aspect. Today, we tend to do that with software, IP tables, and so forth. But in the future, we're going to have to get that more secure because software inherently is compromisable. At the end of the day, our infrastructure must have the security elements to make it happen. And to that end, Google has been doing this in their own infrastructure, as an example on this slide. So microsegmented security becomes a critical aspect, so almost a firewall for every app is a critical functionality of the network that you must be connected to. Then there has been a massive growth in terms of need for adopting the fabric and the network itself in terms of, you see this term called smart NIC. And smart NICs are really a network interface controller plus an FPGA or an NPU that you can create some logic at the point of the data itself, which is the flows of information and packets going forwards, that you can do some specific things to manage and load balance your data center. And so there's been a massive growth in this space by the hyperscalers implementing these kind of solutions. For example, Amazon with Annapurna Lab chips, and you've got Google with their own variant of it, and then you've got Microsoft with their own variant of it. So this type of functionality is now at the top end of the range in the hyperscalers, but the need for driving that capability to everybody and make it accessible to everybody is something else that we've been working at Solarflare to do. So we have started to deliver a set of solutions that we called the smart NIC for the masses. And so our network interface controller today has the functionality and capability to implement many of the features that you would normally find in an FPGA-based or an NPU-based network interface. So we are going to drive that and enable that into the core standard network interface controllers, which is where we think the evolution of the industry is going. So to make this happen, why is Solarflare capable of doing this? Well, one of the key things we've done in terms of our architecture is this very simple diagram here. We have the ability to move at line speed data into our infrastructure, our NIC, our ASIC, and then to be able to take that from the line into a packet, decide what to do with it, whether we need to send it up the wire or down back the wire, we can switch it. And we have these extreme packet engines that allows us to look at that packet and decide to do something with it. Whether we're going to allow it to pass through, whether we're going to capture it, whether we're going to accelerate it, modify it, secure it. So we have this ability to build this capability right into the core of the silicon that's run at line speed. So without any performance degradation, we can run these sort of complicated algorithms within the chip from firmware. This allows us to implement some very interesting application. In fact, our security application is based on this. We have the ability to do 5-tuple lookups on the data and decide what to do with that packet at line speed. And so we can create whitelist and blacklist and policies against those entries and exits of the server. In reality, we are implementing a hardened firewall inside the chip. Not only can we pull this together, but the architecture then says, okay, what happens when there is hundreds of cores coming back to my original thought, hundreds of cores connecting to each other that wants to communicate at the same time. So we've also taken our core packet engine and created 2048 virtual instances of that packet engine. So we can go fine grain all the way down to a virtual instance, down to 2,000 VNICs. So this is some of the key features that we brought together in our technologies that allows us to implement some of the solutions that we're talking about. So if you look at the new server model, one of the key aspects of the new server model is you have these large number of general purpose processing cores as well as GPU cores wanting to communicate with the network. The ability to flow each one of these cores and each one of these instances with its dedicated instance, virtual NIC, and a flow management, and actually to pass it, to change it, to modify it, to send it to the right place or receive it from the right place and send it back to the right area within this micro part of the architecture is a critical aspect of eliminating this issue in the network. So this is the stuff that we pulled together, and we call this Smart NIC fabric. And one point I've got to make here, this is all standard TCP/IP and Ethernet. There is nothing unique about what protocol we put. Whether you're running UDP or TCP, we don't care. It's all the same for us. So we're doing this on a standard NIC, standard Ethernet protocol, and we enable these capabilities to be implemented. All the way from app servers running on neural class connectivity with virtualized environments and containers and microservices, to GPUs, up to 2048 virtual VNICs for every class of microservice, and creating this fabric where every element or every VNIC can have its own firewall, fabric processing, and telemetry capabilities built in right into the hardware. So, if you look at in this example, I'll bring us back to the same problem that we pointed out. How do you scale this infrastructure to a massive enough connections and manage it and stay true to Ethernet? So we've implemented this capability. This allows us, for example, with containers and Dockers, to truly scale in those environments and create an efficiency inside the server that gives you back a lot of the overheads and limitations that you have today. And we are demonstrating that with various proof of concept technologies that are going on throughout the industry. As well as, if you look at those environments, the next thing that comes into mind, how do I create this visibility? So you'll hear a lot of this today in the data centers talking about automation of data center and visibility of the data center. By putting this capability in every NIC that can be installed in a server, we create a complete visibility all the way up to whether you're looking for packets, you're looking for flows, you're looking for telemetry information. Every point where there is this type of capability, we can now do it at hardware, independent of which operating system and software that runs in the infrastructure. So this is what Solarflare is bringing to the wider market. This is what we've been building upon. And really, the key thing here is, in this environment, is we've taken this same concept of very fast TCP/IP, low latency Ethernet, our knowledge of NVMe and TCP, and brought together a plugin that allows us to run NVMe on top of TCP without requiring any specialized networks. And I was going to tell you to come to our booth and see the demonstration, but unfortunately that's not going to happen. But in reality, this is what we're doing. And so we're working with NVMe.org. We've contributed our technology and solution to the working group there, and we are hopeful that in the next few months we enable this technology to happen. And we really want to progress this in the industry because we think this is the right way of implementing NVMe to the broadest masses of the markets, NVMe over fabrics. With that, I'm going to hand it over to Steve, and he's going to talk a lot more about Ethernet.
Oh, you go too. All right, thanks, Amit. So 15 years ago, when I was doing my first startup, Level 5 Networks, we had a technology called Ether Fabric. which was non-coherent shared memory over Ethernet, a bit like RDMA over Ethernet. Great technology, completely the wrong time for it, because fundamentally the networks we were trying to operate in were networks, not fabrics. Etherfabric was not appropriate. Now, a long time's passed, 15 years, and a lot of water's under the bridge and huge developments. So I thought it'd be interesting to revisit this distinction between a network and a fabric. And I'm trying to provide a few examples, not in the storage space. This is a storage community, but it's always interesting and illuminating for everybody to look at what's happening outside, or perhaps tangentially. So if you think of the attributes of a fabric, switch fabric, low latency, low jitter, no frame loss, high bisectional bandwidth. Those are the kind of the fundamentals. And looking at it from a sort of an IP internet protocol perspective, low latency, right? For the last 6, 7, plus years, there's been this huge race to the bottom in terms of latency from the trading community. When you're trading, you are by definition two entities, two organizational entities trading with each other. And therefore you're regulated and required to use internet protocols. And the benchmark performance, or the drag race, is tick to trade, right? Which is essentially a UDP, a datagram-based protocol coming in, and a TCP-based trade going out. And the industry has moved, the trading industry has moved to, first of all, user space protocols. So all of that protocol processing happening at user space. And then even now to hybrid user space FPGA, where the fast path is actually happening down in hardware. And that tick to trade now, for a host-based full software approach, is less than 4 microseconds in out. And for a hybrid hardware approach, it's less than 300 nanoseconds, which is kind of it's just flabbergasting, really. When you start looking at jitter, the two main causes of jitter, certainly that I experience, are caused by scheduling or caused by buffering or queuing. And in the broader network, I think the work that Google's done in terms of addressing buffer bloat has been quite huge in getting rid of buffering throughout many stages in that end-to-end path. And the additional work that they've been doing on TCP BBR is also very interesting, because it takes away loss as being a signal to TCP, and actually makes TCP work very effectively in environments which are lossless. And obviously in lossy environments, it's aimed at improving efficiency, but it can make a big difference in lossy environments. And in particular, in a data center, I think it'd be very interesting to apply TCP BBR, especially because with modern hardware timestamping on the endpoints, where you can get hardware timestamps of precision which is less than 5 nanoseconds, you can actually make very, very good estimates of the round trip time. Bisectional bandwidth, we've been seeing, again, the hyperscale guys operating cloud or factory networks now for over a decade. You can go read the academic papers. That's a done deal. And you see those same architectures appearing either from the looking like at network on the outside, but there's a closet on the inside, or actually you explode the whole data center. I mean, the whole data center is one great big, Facebook-style factory. So it's like, what's the difference at this point, right? In some ways, I think the subjective difference now between a network and a switch fabric is the degree of traffic engineering that's been employed and the quality of service requirements. You can build networks that look like switch fabrics. You can have a switch fabric that looks like a network. Anything else is more like religion. So this line of code here, how many hundreds of thousands of applications have got this line of code embedded in it? A lot of people think this is the top of the protocol stack. It's actually really, a socket, a TCP socket is really about layer 4, really. And that line of code, which I would expect to run for the next, as long as my lifetime, below that line of code in the protocol stack, you've got a huge amount of technical diversity. I'm expecting my code to run on top of, engineered data center networks, wireless networks even. I'm expecting it to run in environments where there's tunneling going on, encapsulation happening at the protocol layer, multiple protocols, different variants of the same protocols. And then inside the host, again, a huge amount of diversity in the operating systems and the places where the protocol processing would happen. So for example, with OpenOnload, the protocol processing doesn't even happen inside the operating system, it happens at user space. And above the socket layer, you've got all the layers, things like orchestration going on, and diversity which is supported by the protocol layering is supporting big waves in the industry, like hybrid clouds and containers and that sort of thing. And so there's huge benefits in fitting in with the model. So we said, hey, why not? Why not try TCP with NVMe? And essentially what we did is we just looked at the observation that says, hey, well, all the NVMe stack requires is a reliable transport at the bottom edge of it. So we glued that to the top edge of the TCP stack in terms of a kernel socket. Now, we use TCP, but we're actually at the top edge of the regular Linux protocol stack, so we could actually use any socket. It doesn't have to be TCP, it could be a reliable form of UDP, that would be fine as well. And beneath that point, you've got all of the different options that you can, or deployment models you could have with the Linux transport stack. So you could be running this guy over the top of a VXLAN tunnel if you chose. And there's an eye chart here, but we wanted to do some quick performance runs, and it ain't too shabby, really. So if you compare on the setup we had, a local NVMe device had got a small block size read half-round trip of about, what was it? Lost it now. 79 micros. Using RDMA, we're at 91, and with TCP, we're at 97. So we're 6 micros off of RDMA on a fabric crossing. When you look at the read-write performance here, I mean, they're all there. Roughly, in very broad terms, the TCP solution that we had was about 10% off of RDMA, but we're in that kind of, I don't know, who cares zone. Now, in some ways, we've built, I said, hey, we just glued this stuff together, but we've built on a lot of innovation to make it possible. If you think back to iSCSI, when iSCSI was introduced, that S-bend, the gluing up of the top edge of the protocol, network protocol stack with the bottom edge of the storage stack, was actually very difficult to achieve because operating system internal architectures just made it hard. The two stacks were very vertically separated. The whole introduction and development of iSCSI forced that S-bend to happen. And so now it's actually relatively easy. It's actually very easy to join the two stacks together in the commodity operating systems. And then secondly, the work that's happened already in the NVMe Fabric working group to implement fiber channel in the RDMA transports has also benefited what we did because they did all the hard work and they made a very nice, clean architecture that was transport protocol agnostic, which was a very nice point for us to glue into. So, the work I presented is essentially, 4 or 5 man-months of effort. That's about it. And as Ahmet said, this work is now inside of the NVMe working group. We contributed Make Open Source. There's other companies who've also contributing, and out of this effort, this joint collaborative effort, I'm very hopeful that there will be a fully standard blessed NVMe TCP fabric implementation. That's my hope for the next year. Thank you. And so, Ahmet's going to finish up, but the future, when you start thinking of how NVMe could be in this wonderful self-driving car, I think the car could be part of the fabric, global internet-based NVMe fabric. And you put the building blocks in place today to make that happen tomorrow. Thank you.
So one of the things I wanted to close, I know we told you a lot of things about what Solarflare is doing, but it's all about Ethernet traffic engineering. We've been doing it for a long while. So I said, how do I close this analogy? How do I make it real to you? One of the things about self-driving cars, well, why didn't we build specialized highways that had all the electronics built in and we can just put cars on there and away we go? That's an impractical effort. Our thoughts is that when you look at it from that perspective and say, why are self-driving cars becoming popular? Because it uses the infrastructure that you've invested in and continues to promote that infrastructure with all the traffic engineering and everything else that's gone to make it. And from our perspective, is like about self-driving cars are implemented to run on any city roads. We think NVMe OF needs to take that into mind and implement it to run on standard TCP that any data center can take advantage of. And this is what we're trying to make. Promote NVMe flash memory to be ubiquitous, distributed, disaggregated storage anywhere in your data center. And that's our mission, and that's what we'd like to help you get there. All right, you can meet us afterwards. We'd be happy to talk to you. And I won't make the joke about the booth, but we'll be around. You can find us. And we're on the net, solarflare.com. Thanks a lot.
Thank you.